Okay, so today we're going to cover radioactivity. Now, I don't mean to scare you, but today's going to be a bit beefier than it usually is. There's going to be quite an in-depth concept that we got to cover today, and unfortunately, there's just a lot of really I don't even know how to put it. It's just there's a lot of like nuances to this that might be a little bit difficult for you to understand. So make sure you're focusing on this one. Make sure you're taking some notes in particular, because you really will want to just make some point form notes just to solidify your understanding. And as always, make sure you're reaching out to me if you have any questions about this. Let's get going. So we're going to discuss how radioactivity works today. We're going to talk about what is radiation, not to be confused with electromagnetic radiation. That's only one type of radiation. There are other types of radiation we're going to talk about today. We'll talk about certain types of radioactive decay. This is where the bulk of today is going to be. This is what gets really difficult. We got to talk about alpha decay, beta decay, and gamma decay. And you will need to know the difference between each one. It's just a big learning curve to it. It's kind of just weird thinking about what each of these are and identifying when they occur, but we'll get to it, don't worry. And then last but not least, we'll talk about some health hazards of radiation. You probably already know a lot of that stuff, but we'll get to it. Anyway, let's go. So first of all, there are four fundamental forces. There are gravitational forces, electromagnetic forces, weak nuclear forces, and strong nuclear forces. Now, these bottom two, weak nuclear and strong nuclear, these are the ones that actually hold atoms together. Strong nuclear are holding all the stuff in the nucleus together. Weak nuclear are the interactions between different atoms. When we have something that decays, what's happening is there's breakdowns in those very strong and weak nuclear forces. You're actually talking about certain atoms actually breaking down themselves. So there has to be some sort of a force that has to overcome these. Now, this list here is actually listed in order from the weakest to the strongest. Not a big surprise when you talk about strong nuclear. That sounds pretty hardcore, right? Gravitational forces are the weakest. Electromagnetics are the next. Then there's weak nuclear, which are stronger, and then strong nuclear, which are the strongest, at least like pound for pound. However, it is possible for any of these other forces to actually overcome these other ones, right? It is possible. It's just in terms of their interaction, that's how it works. Anyway, we'll get to that. So radioactivity. Elements can emit radiation, which are one of three types of rays, okay? There's alpha, which is denoted by this little symbol. It kind of looks like a weird little like fish kind of thing. That's the emission of a helium nucleus, an alpha particle. Remember, an alpha particle is just two protons and two neutrons, okay? When that gets released, when a helium nucleus, an alpha particle gets released by something that's decaying, that's called alpha decay. Beta decay, which is denoted by this symbol, it's like a B that has a really long side to it, that's the emission of a high energy electron. So it's literally just one electron that gets shot out of here, but it's got a high energy, so in other words, it's going to be moving at a very high speed, okay? Then the last one, gamma, which has a symbol that looks like to me it always looked like a backwards lowercase y. It's really weird, and I always have trouble drawing it. But that's the emission of a high energy photon. That's the kind of radioactivity that you usually would think of. When you talk about like nuclear waste being radioactive, it's giving off gamma radiation, right? Which is often literally gamma rays. It could also be X-rays, as long as it's just high energy, right? High energy would mean gamma or X-ray. Another type of gamma radiation, at least I believe, we've never talked about it before, but gamma rays are not the end of the line. There's actually a type of ray that's even higher energy called a cosmic ray. That could also be a form of gamma radiation. Don't quote me on it, though. You can look it up, though. Cosmic rays. Very, very fascinating. All right, so radiation results when an unstable nucleus, we're talking at the atomic level here, unstable nucleus rearranges itself. Alpha and beta decay are the result of an element transforms into another element. So in other words, alpha and beta decay will actually happen if your element decays into something else. Okay, we'll look at that in greater detail in a second. Radioactive decay can be thought of as an explosion, and conservation laws must apply. Four quantities are conserved in radioactive decay. Momentum is conserved, right? So momentum can be measured in many different ways, but regardless, when this quote-unquote explosion occurs, the momentum, the total momentum before has to equal the total momentum afterwards, even if that momentum was zero in the first place. Energy, of course, is always conserved as well. The amount of energy that was stored in the original nucleus still needs to exist somewhere else after this is all said and done. So you have to account for all your energy being the same. Charge has to remain the same. Remember, protons have a positive charge. So if you're emitting an alpha particle, you're emitting 2 protons and 2 neutrons all at once. That's a net charge of 2 positive. There has to be an account for it somewhere, right? It has to come from somewhere. Another thing is the atomic mass number, or in other words, the number of nucleons. Protons and neutrons don't just disappear. There's some really weird things that can happen with them, but they don't just disappear. Something has to happen to them. There has to be an account for where this stuff goes. All right, we're going to focus on alpha decay first. Alpha decay occurs in large nuclei, okay? The nucleus emits an alpha particle in order to transmute into a more stable element, right? Alpha particles, again, are 2 protons, 2 neutrons, okay? It's the nucleus of a hydrogen atom. So write an example of alpha decay. If this was in a printed booklet, you'd see there'd be a blank spot right here. Very classic example of alpha decay is the radioactive decay of uranium. So uranium-238 is going to decay into thorium, which is what has 90 protons. You'd have to look at a periodic table to see that, but the next thing down with 2 fewer protons is thorium. And of course, then it releases an alpha particle. So alpha is the symbol with 4 and 2. Yes, theoretically, you could say it was helium-2, 4, but nobody writes it like that. Because yes, this is an alpha particle, but people just write that as 4, 2. It's the same thing, but please just use this one instead. Notice here how a lot of things are conserved. Your number of protons is conserved, which is really the equivalent to your positive charges, right? So 92 is the same thing as 90 plus 2. Not a big surprise. Your atomic mass number, 238, is also conserved. 234 plus 4. It all stays the same. This picture right here actually shows what's happening with this. Of course, uranium-238 is radioactive. It decays into thorium, which is a little bit more stable, and then a helium. Oh, see, I was saying nobody writes it like that. Literally, someone wrote it like that right there. See, I didn't even notice. Hey, don't write it like that. I want to see you write it like this instead, alpha particle rather than helium like that. Anyway, the reason this happens, as messed up as it is electromagnetic repulsion. So the positive and negative interactions becomes greater than the strong nuclear force for these really large, unstable nuclei. If you look at a periodic table, all of the ones with really large nuclei, so all the ones that are at the bottom, they're not really stable. They're all radioactive. And they're radioactive for a reason, because at this point, there's so much charge going on that your strong nuclear force just can't contain it anymore, right? Yes, strong nuclear force, pound for pound, is more powerful than electromagnetic forces, but there comes a point where even electromagnetic force can punch a little bit harder, right? I'm oversimplifying this, but hopefully you're getting the idea. All right, next up, beta decay. This one is weird. This one is really, really weird, okay? So buckle up here. There's 2 kinds of beta decay that we need to talk about. Now, beta decay, no matter what type it is, beta decay occurs when a nucleus decays by emitting an electron, okay? So an electron is produced, and it's always got high energy. There are 2 types of beta decay. We call the one beta negative. Sometimes people call it beta minus. It's the same thing. And beta positive. Sometimes people call it beta plus. It's the same thing, okay? We'll talk about beta negative decay first. In beta negative decay, a neutron transforms into a proton, an electron, and then an extremely small neutral particle called an antineutrino. And the symbol for that, yeah, I know how messed up this is getting. I warned you at the start of the day. Antineutrino has a symbol of a V with a little bar on the top of it. We'll break down what that bar means a little bit later. You know what? Forget it. I'll do it right now. Okay, really buckle up here. In reality here, there's matter. I'll write it up at the top. There's matter. That's all the stuff we know. All the things, you know, protons, electrons, neutrons, all the atoms and molecules we know are matter. But then there's something else called antimatter. Which sounds like science fiction, but it isn't. Antimatter is like the opposite equivalent to matter. If you looked at what antimatter would look like, it probably would look exactly the same thing as matter. But the weird thing about antimatter is if antimatter ever touched matter, they would annihilate each other. And then they would just transform each other into raw energy. So there'd be some huge explosion and they would just disappear from reality, but that energy that made them up would be released. So it would be a big explosion. An antineutrino is a form of antimatter. The bar on the top here would tell you that you have antimatter. We'll get into that in way greater detail later on, but just so you know. So in beta negative decay, the atomic number actually increases by 1, but both mass and charge are conserved because they always have to be. An electron emitted from the nucleus is called a beta particle. So a beta particle is just another way of saying an electron, right? And it's written as this beta symbol with a 0 on the top because there's 0 protons or neutrons, and a -1. So it's like got -1 protons. What really that means is it's got a -1 charge in equations. So write an example of beta negative decay. This TL, I think is that thallium? Hold on, let me just double check here. Yeah, it's thallium. I just wanted to be sure without saying the wrong thing. So thallium 208 can actually undergo beta negative decay. And how it works is it's basically going to turn one of its neutrons into a proton. So a neutron becomes a proton. So notice how your proton number goes up by 1. Your atomic number, however, your atomic mass number, I should say, sorry, your mass number doesn't change though, because even though you lost a proton, you lost a neutron but gained a proton. Wow, I'm not doing well today. This number would still stay the same. Okay. If we're going to do some quick math on this one, just to really illustrate this point, 208 minus 81 tells us this guy has 81 protons and 127 neutrons. Okay, but this guy has 82 protons, and 208 minus 82 would be 126 neutrons. Okay, so we just turned a neutron into a proton. Now, in order to keep our charges all the same, because remember, otherwise this would have one more positive charge, we had to release a negative charge. So in other words, we had to release an electron, and this anti-neutrino actually is just something that gets produced by breaking down a neutron, because a neutron isn't just a proton mixed with an electron. That's not how it works. A neutron is made up of a bunch of different things, and an anti-neutrino gets released. So yes, believe it or not, antimatter can be produced just by some simple process like this. Now a neutrino or an anti-neutrino, those are really, 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 really small. We've never talked about them before. They are way smaller than even an electron. We'll get into that way later on, believe me. Anyway, moving on. So here's an example of beta negative decay or beta minus decay, as the picture shows. Carbon 14, right, with 6 protons and 8 neutrons. One of its neutrons becomes a proton, so it becomes nitrogen 14. It changes what it is because the proton number changed. It went up by 1, and it has to release an antineutrino and an electron, or in other words, a beta particle. Okay, moving on. Now, the other form of beta decay is the less common beta positive decay. And this one, if you thought beta negative decay was weird, buckle up on this one. In beta positive decay, a proton transforms into a neutron. So it goes the other way around. And something called a positron, which is actually a form of antimatter, and a neutrino, which is just a form of normal matter, are also released. Write an example of beta positive decay. Well, here's one. It's kind of the reverse of that picture we just saw on the last slide. Let's say you had nitrogen 13, right? So just regular old nitrogen. One of its protons turns into a neutron. So your proton number goes down. This thing right here, beta particle with a 1 right here, that might look like it's a proton because it just says 1 proton, but really what it's talking about is its charge. A positron is the antimatter equivalent of an electron. So a positron is basically an anti-electron. That's basically another way of thinking of it. Okay, it's not the same thing as a proton. It is an anti-electron. It functions like an electron, except it's got the opposite charge, and it's an antimatter equivalent to it. During alpha and beta decays, the initial nucleus is referred to as the parent nucleus, and the resultant nucleus is called the daughter nucleus. So regardless of whether you're doing alpha or beta decay, your parent is your original one, and your daughter is the product, okay? Okay, here we go. Electron capture. Electron capture can also occur, which is when a proton-rich nucleus captures an electron to become more stable. The process is the reverse of beta negative decay. Write an example of electron capture. So basically, like let's say we had aluminum 26. If it gained an electron, what could happen is it can actually like more or less merge with the proton to make a neutron. And so that bumps down the proton number down to 12, which makes us now magnesium. Still has the same atomic mass number though, because the number of protons and neutrons is the same. And it produces a neutrino. So there you go. So basically, a proton and electron combine to make a neutron with a neutrino released. Just another thing to know. All right, told you it was going to be weird. All right, gamma decay. I honestly don't think gamma decay is anything as weird as beta decay, but here we go. In gamma decay, a high energy photon, or in other words, a gamma ray, generally speaking, it can be an X-ray as well, or even a cosmic ray, I believe, but gamma ray is the most common, is emitted by the nucleus, but the nucleus does not change. This is what's so suspicious about this one. When you look at the formula, it looks like really, really boring. So gamma decay often follows alpha or beta decay because the nucleus is left in an excited state and it emits a gamma ray in order to drop to a lower, more stable state, okay? This is kind of like the idea when we talk about like those energy levels with all the bars and stuff. It wants to drop back down. So it wants to release a photon to become a bit more stable. That's basically what's happening here. So with gamma decay, one thing that's important to know is that your atom itself doesn't actually change what type it is. It just changes how much energy is stored in it. Okay, so it just releases some energy, so it's a little bit more calmed down. So an example is if you had carbon-12, it's going to become carbon-12, but release the gamma ray. So in other words, this carbon-12 right here is just less excited than this one. It had less energy in it than the original parent nucleus. Okay, so again, in the formula, it looks very uninteresting. Keep in mind, however, that the amount of energy that can be released through this process can be millions of electron volts. There's a lot of energy that can be released, especially for the bigger particles that can be released in one of these processes. It's quite incredible, actually. All right, next up, decay series. You don't need to know this one too much, but it's just nice to know. The graph kind of helps. Many isotopes are radioactive and many decays may take place before a stable isotope remains. There are no completely stable isotopes with an atomic number greater than 83, just for your information. So kind of like I mentioned before, all the ones at the bottom of the periodic table, none of them are stable, right? This is called a radioactive decay series and is often represented in graph form. Basically, all you need to know from this is if you have something originally, it's going to undergo tons of different decays, alpha, beta, and sometimes even gamma, to eventually become something a little bit more comfortable. So what to interpret this chart here, what we're starting with is uranium-238. So uranium-238 is right here. Notice it undergoes an alpha decay, and then it undergoes a bunch of beta decays. That brings it actually back up to uranium, because remember, it's dependent on your number of protons, or in other words, your atomic number. Brings it back up to uranium, and once you have uranium-234, then that one goes, okay, no, I really need to undergo a bunch of alpha decays. So it goes under a bunch of different alpha decays and a whole bunch of different series. All these different processes happen, and then you got some choices down here depending on a bunch of different scenarios. You can undergo more alpha decays, you can undergo some beta decays, any combination of which, and eventually it gets down to some of these more stable ones, like mercury, thallium, or lead, right? Which again, lead is about as high as you can go without getting unstable. So all these ones with 83 or more, these are all unstable, so they always break down. You don't need to know it in great detail, but just kind of an FYI. All right, moving on, magnetic deflection of radiation. The following image is a reminder about how these rays are deflected when passing through a magnetic field. This comes back down to the idea of cathode rays. Remember, cathode rays are just charged particles. Under alpha decay and beta decay, you're producing an actual particle. It's like a cathode ray, right? So in other words, alpha particle, you can hardly see that there, but alpha particle, that's a, well, it is an alpha particle. It's got 2 protons, 2 neutrons, so it's charged. It's got a positive 2 charge. That's going to be deflected by a magnetic field, okay? Beta decay is an electron, right? Or I guess a positron if you're doing beta positive decay, but it's still going to behave a similar way, right? When it's going through a magnetic field, depending on how much energy, it's going to be deflected in different ways. Gamma radiation, however, remember, gamma radiation is electromagnetic radiation. It's not affected by magnetic fields. Cathode rays are. Cathode rays are the actual, like, charged, actual, like, physical matter particles, whereas gamma rays are not, because gamma radiation is not necessarily matter. It's just electromagnetic radiation. So it's not going to be affected, or not going to be deflected, I should say, by that magnetic field. All right, so hazards of radiation. This is where we're going to get a little bit simpler here. Radioactive decay produces particles which can be harmful to living tissue. These damaging effects are not, however, immediately seen. There's 2 major types of risks. There's radiation sickness. This is where radiation ionizes cellular material, disrupting your biochemistry. Large doses can kill cells, especially blood cells and intestinal cells. Symptoms would include nausea, bleeding, vomiting, diarrhea, headaches, inflammation, and then eventually, of course, death. Radiation sickness is what people would get if they were exposed to nuclear waste. And again, this is not immediately seen. Radiation sickness, or acute radiation sickness is what it's often called, is quite scary because you often will start seeing things a little bit later, like within a few days, and then the symptoms just get completely out of control. Now, if you have severe radiation sickness, yeah, you're going to have immediate burns, and it's going to be like immediately bad. If you've ever seen the HBO documentary Chernobyl, by HBO. If we were still having in-school classes, I'd be pushing for us to watch a couple episodes of this. It is a fascinating, although yes, somewhat fictionalized look at the Chernobyl disaster in the 1980s in the Soviet Union. But again, radiation sickness was a big part of that. A lot of people died from this. Another thing that can happen, however, is genetic damage. This one's more common. It's more like from like sustained exposure. So high energy particles and gamma rays can alter your DNA at like at your absolute core DNA level, right? This may lead to cancer and mutations. This often happens between 10 and 15 years after exposure. So what they often found was, let's say even in Hiroshima, which of course was the Japanese city that was bombed during World War II with an atomic weapon, anyone who survived that often found that several years down the road, they end up developing certain mutations or cancer. And that was again because they experienced genetic damage from the radiation from those nuclear weapons. Now, although there is a natural background radiation, like right now we are being hit by tons of radiation, it's usually in small enough amounts that the body can defend and therefore heal itself, right? So even though, yes, some gamma rays and stuff do pass down to the surface of the Earth, and you are being bombarded by it at all times, it's not really a big deal. Where we are, you know, we can accommodate to it. But again, you know, there can be some issues in the long term. So the damaging effects of radiation on living tissue depend on three things: the energy it carries, the ability to ionize atoms, and the depths to which it can penetrate tissue. So higher energy, of course, is going to be bad. Clearly being bombarded by gamma rays or X-rays is going to be a really bad time. Even ultraviolet rays, hence why sunburns are a thing. Ultraviolet rays can be damaging after long periods of time. Of course, we know that sustained exposure to ultraviolet rays can cause things like skin cancer. But again, the higher energy it carries, the worse it generally is going to be. And again, all of these correlate to the amount of energy it carries. So kind of a silly example. All right, so breaking down the different types of radiation. If we had a normal class, I'd be getting you to jot this table down. I wouldn't worry about it though. Alpha radiation travels only about 5 centimeters in the air. It doesn't go very far, right? So those alpha particles don't really move too far, and they cannot penetrate skin. This column here is talking about the ionization of parent nucleus, not the ionization effect of the actual particle. Alpha particles don't really ionize things too well. They can, I suppose, technically, but they are formed by a very strong ionization of the parent nucleus. Clearly, they're losing 2 protons, so there's quite a significant charge. The health hazard, however, of alpha radiation is quite low. Beta radiation, on the other hand, travels about 30 centimeters in the air, so about a foot, and it can penetrate only about a centimeter into your body. This is caused by just moderate ionization of the parent nucleus, but the health hazard of beta radiation is still low. Like, I mean, technically, if you were hit by beta positive decay, it's, you know, there's antimatter collisions, but since it's only a positron, it's not going to release a lot of energy. It's not going to be a big deal. Gamma radiation, however, this is the scary one. It travels great distances in air. And of course, because it's emitting a gamma ray, it's traveling at the speed of light. Gamma rays will go right through your body. They're even more effective than X-rays, of course. That's why X-rays are used in doctor's office. You get like one little burst of an X-ray. Those X-rays travel right through your body. A screen picks it up, of course, and that's how you can see your bones and stuff, because your bones might actually deflect them. Anyway, the ionization of the parent nucleus is low. However, the ionization potential of gamma rays on your body is very high. So that's why I don't really like this column here, but the health hazard is very high for gamma rays, of course. That's where you get some very serious side effects. All right, so we're going to run through a few examples here. Determine the daughter element that results from the alpha decay of radium-226. So this is where we're really getting into the important stuff here. You will need a periodic table when you're doing these kinds of questions. I would highly advise, if you don't have one in front of you right now, please go pause the video here and go find one. But anyway, we're dealing with radium-226. You have to find radium on your formula or on your periodic table here. It's in the bottom left-hand corner. What we need to understand is that this is going to be undergoing the process of alpha decay. Okay, so alpha decay again emits an alpha particle, which is a something with 2 protons and 2 neutrons, so 2 and 4 being the numbers that are in there. If we're starting with radium-226, looking at our formula sheet, we can say that we have radium-226. We have to determine the atomic number based on what's given on the formula sheet here, so 88. It's going to undergo alpha decay. Alpha decay just takes this and it decays into something where we drop our proton number by 2. On your periodic table, we're looking for something excuse me, we're looking for something that has an atomic number of only 86 rather than 88, right? So find it on the sheet. You're going to find it's actually radon. So radon, which is in the kind of on the right-hand side of it, that has 86. Notice before I even write any other numbers, I'm going to write my alpha particle next. It's got 2 and 4. So that means we have to take this number and drop it down by 4. That means on my radon here, it's got to be 222. So notice all of these numbers along the top add up and are balanced on both sides of this equation. And my atomic number, which is protons, also adds up along the bottom here. So that right there would be the alpha decay equation for radium-226, and the daughter element would be radon-222. So there you go. All right, next up. What element will the beta-negative decay of thorium produce? Okay, so thorium, if you find that on your formula sheet, it is, let's see here, thorium. This is kind of embarrassing when I have to like scout my way through it, but again, I haven't got this memorized. Okay, it's like way down in the bottom left-hand corner. Thorium has an atomic number of 90. Now, what's kind of weird about this is it didn't tell us what kind of thorium it is. Like it just didn't say, oh, it's thorium, 232 or whatever. So we can't assume a number here, but the good news is in beta-negative decay, it doesn't matter. So I'm just going to put an A here, right? Because that's usually what it is in the general form. So thorium is going to undergo beta-negative decay. Beta-negative decay turns a neutron into a proton. Sorry, not plus, arrow, sorry. Turns a neutron into a proton. So what that means is we need to take our proton number and make it go up by 1. So it's going to be 91 now. 91 is our proton number. That means we're going to have protactinium, which is the next thing on our periodic table, so Pa. The atomic number is not going to change here, so I'm just going to leave it as A. And then, of course, we're releasing a beta-negative particle, which is literally just an electron, but we write it as like a beta particle with a -1 down here and a 0 up here. And then don't forget beta-negative decay. Beta-negative decay produces an anti-neutrino, so plus V with a little bar on the top, okay? Now, it's asking us what element will that produce. The element that's produced is this guy right here. So writing it out, it is protactinium. There we go, spelled it right, I think. Yeah, protactinium. And we don't know what the atomic mass would be, but it would be whatever the same atomic mass was on the thorium. So I'm just going to stop right there and say it's protactinium, and we are done on that one. All right, we've only got a few more questions we're going to do here. Identify the type of decay for the following transmutations and write out decay processes. So this is where you got to kind of analyze what's going on with your numbers down here. So notice our number of nucleons is not changing, so our atomic mass number is not changing, but we lost a proton. That tells us that there's got to be some other proton piece that's got here. Well, the only one that's got this is the one that has like a 1 out here, which is going to be beta positive decay is what I'm getting at here. So we know, first of all, it lost a proton, yet the nucleon stayed the same. So that means we have beta positive decay. And we want to write out the decay process itself. So we'll say it's 54, 25, and then becomes 54, 24 Cr plus our beta positive particle. So 1 beta 0. And then remember, beta positive decay produces just a regular neutrino, so plus V. So there you are. That would be your solution there. In terms of how I solved that one, guys, like you might be really scratching your head right now. You might even be crying right now. I don't know what's going on. Sorry, but really, it's just a matter of analyzing your numbers here. And remember, everything has to balance out. Your atomic numbers along the top have to, your atomic mass numbers on the top need to balance out, and your atomic numbers on the bottom also need to balance out. Beta decay is the hardest one. Honestly, that's the one I scratch my head on. But just know that beta positive produces a neutrino. Beta negative produces an antineutrino. Beta positive decay, this is not a proton here, but rather this is a positron, which is a type of antimatter. Again, I warned you at the start of the day. You can't complain. I told you it was going to get weird. All right, last question here. Identify the type of decay for the following transmutation. Okay, so same idea here. Oh, this one's not too bad. Notice what's happening to our number down here. It's going down by 2. Well, as soon as you see something going down by 2, that right there can tell you this is an alpha decay, right? Because we lost 2, so we had to have another 2 get released. This is just regular old alpha decay. I'm not even going to write out the formula again. That's all you got to put on there. That's alpha decay. Done. See, it lost 2 protons, and also you can even look at your atomic mass number, lost 4 nucleons. Yeah, it had to be alpha decay. So that one wasn't too bad. That's the last one that was in there. If there was a question again where this thing didn't change, that would tell you it was gamma decay. Okay, so just make sure you understand all the difference between those two, or between those 3 types, or 4 types really, because beta positive, beta negative. Anyway, we're done. So for an example, I'm going to say example. For practice, I want you to work on your atomic physics assignment, and I want you to try the radioactivity worksheet, which is page 44 in the booklet. Please make sure you're reaching out to me if you're stuck on this stuff. I understand this is not simple by any means. Some of you might just get this right off the bat. It's just a matter of accepting what these things are. I know it's obscure, but please make sure you're letting me know if you need any help. Best of luck.